Mm. Mm. All right, Clive.
Hey, Governor.
Hey, Hubert, how you doing? Hey, Grace.
Hi.
Hey, Luis, Jose.
Sorry. How you doing, guys?
I'm doing good. How are you?
Good, man. Good. Take the charge. All of them. All of them. Just put the whole thing. Yeah. And take it to you. Okay, go to your room. Okay? Make sure you plug it. No, Ben. You don't grab it from there. Grab it from here. Okay. How you doing, sir?
There he is.
What's up?
Come on, man.
Hey. Can you hear me?
Yeah, we can hear you.
Yeah, I'm good. Oh, that.
Here. Kevin's here. Lewis is here. Chris is here. That guy ain't here. That guy's here. That guy ain't here. Okay. How'd you do on the homework?
Oh, it wasn't horrible.
Horrible.
Some of it's a little different, but
Let's go through it here. Hang on, let me look at something real quick. What the? Hmm. So, Okay. Chapter 14, homework. Waveform angle at 360 degrees represents the time for one
Cycle.
shout it out.
Yeah, that's a cycle.
Cycle.
Yep.
If you guys had trouble with any of these, if you couldn't find it in the book or anything, let me know. But I'm just gonna run through it. Good grief, leave me alone. Okay. Oh, that's pretty good, fellas. How'd I do?
Good. I'm a professional.
Yeah, thank you. Okay, so the angle from A to B here is 360 degrees. What would be, if this is 0 degrees
Mhm.
and this is 360, this point would be,
180.
yeah, yeah, yeah. And then, of course, the peak here would be at 90.
270.
The peak here would be at 270. 360 degrees represents one cycle.
Mhm.
So then what happens after this point?
Go back to 0.
Just frickin' starts over. You know what I'm saying? There it goes.
Yeah.
Do it again. Now, how many times does that cycle happen per second?
Uh,
Six-
60.
60 times a second, 60 hertz. That's what Amarin
Yeah.
gives us from.
Mhm.
Yeah,
He puts up
60 in
wall.
United States and 50 in I think Europe.
Yeah,
Something like
they,
that.
they run it weird, 50 hertz, and they do 240 volt and all sorts of weird stuff over there. This here's America. We do 60 hertz. You know what I'm saying? Anyway. All right. So that is one cycle. Quantity that has a magnitude and direction.
Or
What?
C.
Sinusoid?
Phasor.
Phasor?
That's getting into physics a little bit, but we'll use phasors in talking about the relationship between capacitance and inductance. But a phasor looks something like that, and it has a direction, and it also has magnitude or units. So this could be a force, it could be a voltage, it could be a current, it could be I don't know, inches. It could, it's got some kind of unit and it's got a direction. And you'll see how we use this later on, but this is kind of a physics thing. This is a phasor. So if this sine wave up here is now I'm not going to get into that. I'm just going to leave it at that so we don't confuse things. When two waveforms are exactly out of phase, what's the difference in degrees?
Uh,
90.
Nope.
oh, it's
And
it's, it's 90? No.
Nope.
No, it's 90. Oh. Let's do 70.
Nope.
Oh, Oh, so I don't think I read, but I'm not sure.
Okay. You guys have, in your home, what's the voltage you get when you plug something into the wall?
Mm-hmm.
What is that voltage?
There's a,
About 280.
120 volts.
120.
Here's the sine wave for 120 volts. That value is actually the RMS value. It's somewhere in here. We'll talk about that in a minute. But you get 120 volts, and that is taking your meter and checking, draw a little outlet here. Okay. Pretty outlet or smiley face or however you want to look at it. But this, if this is a receptacle and outlet, you know which wire this is hooked up here in the back behind it? That's the neutral. And that neutral is referenced to ground. Okay, it's almost like a designated ground that you use as a return path for the circuit to work. If you put a meter, your digital multimeter, if you put a lead in there and you put a lead in here, this one is actually giving you the sine wave. But the difference of potential between this point and this point is 120 volts. You guys talk about difference of potential at all in your other classes?
Yeah, a little bit.
A little bit?
Yeah.
Here's how
okay.
here's how I look at it, or I teach it. Some of you might remember this from physics in class, but this is a big old freaking boulder, okay? Sitting on a hill. And it's big, so this is a person, right? It's sitting on a hill. Here's the hill,
Mhm.
okay? Is there this potential energy versus kinetic energy? You remember this from physics class?
Yep.
Does this boulder have potential energy or kinetic energy?
Potential at that point.
Potential, because it's not doing anything. Kinetic energy is if the boulder is right here and it's going down in a hurry, right? That's kinetic energy. There's stuff happening there. Okay. The difference of potential between here and here is something we read in voltage. It has the ability to produce energy. And let's say, for instance, that this example we're using is 120 volts. This would be the hot or L1 or line 1 or hot or whatever you want to call it. And then this thing is referenced to ground. And don't let it confuse you that this is ground. You know, it's the bottom of the hill. But you have to have 2 points to read difference of potential. Okay, this is the symbol for ground, by the way, if you didn't know that.
Mhm.
So in this case, at your outlet, this neutral over here, the longer slot is always the neutral, or it should be. That is always referenced to ground, and then this is your hot. That's your sine wave. So if you're reading that sine wave on your meter, you're reading the potential of this sine wave to produce energy with a reference to ground. Okay, now where I was going with that is in your home, Ameren also gives you the ability in your panel to have 240 volts. That's twice the voltage of this. And that sine wave, when you get between two phases that are 180 degrees out of phase, it looks like this. Let me see if I can explain this to you. With 120 volts, we would put our meter lead on this phase somewhere. And again, we're reading this 60 times a second with a reference to ground. when we're reading 240 volts, and different, we're reading this phase to this phase. Okay, and anywhere on this sine wave, I guess what you're actually picking up with your meter is this value here.
Okay.
That is 240 volts. Okay, what you end up getting is like alternating current. Let's put a little simple circuit here. Alternating current, light bulb. If this was a battery instead of DC, what would the current do? It would only go in one direction,
Yeah, one go around.
right? In alternating current, you're getting current going this way, and then you're getting current going that way. And that happens 60 times a second. So when you have two different polarities happening at the same time, and the difference between them is 240 total volts, I think of it this way. You got positive direction this way, a positive force this way, and a negative force in this direction. So they're acting the same way. So it's almost like a push-pull, right?
Mhm.
So think of the blue phase. I'm just going to use, oh boy, what the? I'm going to use eBay as an example, okay? eBay's standing here. And I'm right here. I'm the blue phase. And Chris is over here. Chris is the red phase. If it was just me pulling on his arm this way, he'd get 120 volts. If I'm pulling on his arm this way and Chris is pushing on his arm that way, he's got 240 volts in that direction, correct?
Yeah.
And then after one alternation, I start pushing and Chris starts pulling. It's a lot more force, right? Voltage is force, electromotive force. If you add those two directions, but one's a push and one's a pull in the same direction, you get 240 volts. Anyway, that's a lot of spiel about alternating current, but my point was to show you that if these two are exactly out of phase, they're 180 degrees out of phase. Am I making sense or is this confusing?
That makes sense.
No, no.
The value right here is just a random value, 100 volts. This value would be exactly negative 100 volts. Makes sense? Add
Yeah.
those two up, peak to peak, what do you get?
But with respect to the ground, right?
With respect to each other, add those two up and what do you get? You get this amount.
To respect each other, and it's not respect to the ground.
I'm just saying with these two phases, the
Oh,
solid line and the dotted line, if you add them together, what do you get?
200.
200. Yeah.
200, because the polarity is opposite. One's a push and one's a pull. They're pushing and pulling in the same direction. See what I did there? Can you see me?
Okay.
You can see me? What am I doing?
You're dancing.
I'm dancing. All right. I'm just checking to see what's going on. Okay. Bloop. Current variations are in phase with the applied voltage in an AC circuit with Remember that one?
Current variation, current phase.
Another way to ask this question would be, what type of circuit would have current and voltage in phase with each other?
What type? No, I don't get it. Sorry.
The answer to this one is resistors only. So in a purely resistive circuit, where I'm going to draw some phasors here, this might not all make sense yet, but it will the more we get into capacitance and inductance, okay? If this is current, and this is voltage, they are in phase with each other. What that means on a sine wave is if this is your voltage, and this is your current, they're exactly in phase with each other. It just means that the sine waves line up. Okay, so they cross at the same point here, here, and here. That is in a purely resistive circuit. So think of it this way. An AC circuit with only a resistor in it. Okay. What ends up happening that we'll find out in future chapters is if you do something like put in that same circuit, you put a capacitor in here. If you put a capacitor in here, this sine wave starts to shift a little bit. And you'll see that the points are all the same. Well, no, they're not. I know my drawings really sucks, but
Got it.
they start, you put a capacitor in them there and they start to move. They become out of phase with each other, okay? So this
Yes,
corresponds to this sine wave. What?
sorry. So the capacity affects both voltage and current, or just voltage?
The point is that in a purely resistive circuit, so if I take
Mhm.
this out of the circuit and there's only a resistor in there, the sine waves will be in phase with each other. So one is voltage and one is current. If I add a
Okay.
capacitor or an inductor, which this is
They
future
change.
chapters talking about, you don't need to worry about it right now. But the point is that if you add a capacitor or an inductor, the sine waves shift a little bit and they become out of phase.
Okay, okay.
Mhm.
Follow?
Yeah, got it. Thank you.
And just so you know, that's when you start to see phasors that look like this. Okay, so they're no longer in line with each other like this one is. See what I'm saying?
Mm-hmm.
Throwing a lot at you, but a lot of this stuff is future chapter type stuff. Anyway, the point of the question though is if current and voltage are in phase with each other, it's only a resistive circuit. There's no capacitors, inductors. Okay. Which
Okay.
of the following is a non-sinusoidal, not a non-sinusoidal waveform?
Cosine wave.
Cosine. And that just probably come out of straight out of the book, right? Give you some examples of waveforms, and cosine waveform was probably just made up for a question. Number of cycles per second is the frequency measured in what value?
Hertz.
Hertz. Not Gilbert's. One complete revolution of an AC waveform is?
Uh, Pulse.
So from here to here, one complete revolution, 360 degrees. What's that called?
Cycle.
Cycle? What's a half cycle called?
Alternating.
Alternating. That would be this point right here. Why do you think it's called an alternation?
Wave.
It changes polarity,
Yeah.
Okay.
right? So remember our example with eBay and me and Chris pulling and pushing on them?
Mm-hmm.
At this point, if it was just me, in this direction, I'm pushing eBay, and in this direction, I'm pulling on them. So the current is going in the opposite direction. So it alternates right here at this point. What symbol is used to represent the ratio of circumference to the diameter for any circle?
Pi.
Pi. Maximum value of an AC waveform.
Peak value.
Peak. You'd think that by the end of the semester, I'd be really good at drawing, sine waves, right?
Mhm.
Probably not.
That one's pretty good.
Who said that?
I did. That one's
Extra credit.
pretty
Extra
deep.
credit. Somebody
Yeah.
give me a flattering comment. That's pretty good. Yeah. Uh, so we got alternation. Peak. What's this one called? The Gilbert? No, that's the other peak.
Yeah. Peak to the negative. Mhm.
For a complete sine wave, the average value is
0.707.
1.414. Technical.
this is the average value, okay? Which means if we took a reading here, 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 and we averaged them all out, it would equal 0,
Mhm.
right? Because if this is plus 1,
Yeah.
this is minus 1. If this is plus 2, this is minus 2. So one full waveform would give you an average of 0.
Let's see where this goes.
To convert a peak value of AC voltage to RMS.
Mhm.
So if this peak was 100 volts, what would the RMS value be?
Multiply by 0.707.
It would be times 0.707. Okay, so here's RMS. when you put your meter into an outlet on your wall, what does it tell you the voltage is?
It's usually somewhere between 110 and 120.
Yeah, it's supposed to be 120 volts. That's what Ameren's supposed to be giving you. That value is actually this. Or no, excuse me, it's this.
Yeah.
Why do you think that is?
Mm,
The answer is it's not an average, okay? Well, it is an average, but this magical 0.707 number is actually a percentage. So about 70% of peak. Okay, so when your meter is reading the difference from the hot and the neutral of your outlet, it's reading this blue line, okay? And what you're getting there is sort of an average of the potential energy there, okay? Peak value is right here, but the usable voltage, okay? So if I stop this sine wave anywhere along here, I'm just gonna pick a magic spot right here. If I stop that sine wave right there, what is the voltage? It's this, right? That's way less than 100, right? If I
Yeah.
stopped it here, that's way less than 100. If I stopped it here, it's like, I don't know, 95. But during the course of time from here to here, you average about 70% of the peak value. Does that make sense? It's the usable voltage. So even though that sine wave gets all the way up to peak, if I put a multimeter on this circuit, I'm going to read about 70 volts, 70.7 volts. That's what the RMS value is. RMS stands for root mean square. It's just a way to derive the average value of a sine wave like that.
Yeah.
What are you doing? Are you twirling duct tape?
Yeah.
Oh, okay. It's totally random. Okay. So if you were converting peak value to voltage, you would multiply the peak value times RMS times 0.707. But what if I had an RMS value and I needed to convert it to peak?
You divide.
There's a couple ways you can do it. So if I'm given an RMS value of, let's say it's 50 volts, and we want to find what the peak is. There's a couple different ways you can do it. You can take 50 times 1.414, or you can take 50 divided by 0.707. Anybody got a calculator handy?
Yeah.
35. 35.
You say 35?
Oh, I multiplied the 0.7, never mind.
It shouldn't be right. Be more than
70.7.
Yeah, 70.7.
0.7 volts. In this case, if I gave you 50 volts RMS, could you tell me what the peak to peak value is? So that would be
140.
this.
One 41.4.
Oh, it's double the,
Nope. It's just twice the
twice the peak.
141.4.
So it's 70 times
Oh.
2.
Like on a lab, you might get, what's the peak value? So VP would be 70.7. What's the peak to peak value? That'd be V peak to peak would be 141.4. It's just twice this. I want to pause for a minute and look at remember from the other day, I told you I was going to put a different formula sheet on there for you.
Mhm.
Here it is. Take this and download it and open it up. It looks like this. Actually, when you open it up, it actually looks like this. If you printed it out, it'd be in landscape, not portrait, but I'm gonna rotate it so we can read it. I want to see if peak to peak is on there. Oh boy.
Good stuff here.
But the big on here is you see these phasers.
Mm-hmm.
So these are your phasers, and then you see in a purely resistive circuit. So this middle one, how the sine waves between voltage and current are lined up. And
Yeah.
remember before we were talking about, well, if you add a capacitor to the circuit right here, that sine wave shifts a little bit. I think I drew
Yeah,
this, but this is kind of a little bit better of a picture. You can see how those sine waves don't line up anymore. Anyway, that's what that is talking about. So if you had this formula sheet in front of you, on here somewhere, I would write down maybe I'll do this for you guys when you're taking your quiz. Would it be helpful if I printed this out for you to use on the quiz instead of looking at it online?
Oh, yeah,
So, yeah.
they will help. Yeah.
All right. So when you get your formula sheet, here's what I would write down on there somewhere.
Thank you.
I would write down V RMS equals V peak. Whoops. Times what?
Times 2.
707.
Nope.
No, oh,
V
okay.
RMS is here, right?
Okay, okay.
0.707.
Times 0.707.
Mhm.
The peak equals the RMS. You can say times 1.141. You can say divided by 0. Either way, you're going to get the same number. But I'll say times 1.414. And then V peak to peak equals what?
Equals
2 times peak.
V peak times 2. So if it's me, I'm taking my formula sheet and I'm writing those things down.
just hold a second, please.
The VPP is that's just the 2 peaks together, added basically. Bottom and
Can you
top.
say that louder, Corey?
Is the VPP is that the 2 peaks added together basically, like the top peak and the bottom
Yeah.
peak?
Yeah.
Yep, it's V peak to peak.
Okay.
This P dash P means peak to peak. Pete. Peak to peak value. Length of one complete cycle.
Wavelength.
Yeah, that's a wavelength.
Length. Quantity that varies in time.
Phasor.
Yeah, phasors.
Phasor. An important characteristic of DC pulses is that their on and off times are
Often different.
Off more than on.
They're often different.
different.
Okay.
What is the ratio of a DC pulse's on time to its period?
Duty cycle.
What is the term used for the indication that a DC pulse is on?
Wavelength. Wavelength.
No,
Is that pulse width?
pulse width. For a second there, I'm trying to think, why did we include this? Why did I leave this in your homework? Because you won't see it very much in the labs, but it is important. So where you have a sinusoidal waveform, you might also get some kind of a waveform that looks like this.
Yeah. What?
So that's a square wave. Back up a little bit. So question 16, these pulses have on and off times that might be different. So you might have, half a second here. You might have a quarter of a second here. Or then you might come up and have a small time. And then you might come down and have a long time. The ratio of the DC pulses on time to its period would be the ratio of this to this. Okay, so this from point A to point B here, what's that called? The period or the cycle,
Cycle. Yeah, wave cycle.
right? So if this was halfway, the ratio would be 0.5. I don't think you're gonna have to do any calculate. Well, we'll see. An instrument that displays signals in a time domain
Oscilloscope.
Oscilloscope. Do you guys use oscilloscopes in 131 or 132 at all?
Yeah, a little bit.
Yeah, a little
You
bit.
get introduced to
Who is-
them at least?
Well, just a demonstration of how to use it.
Yeah. What the oscilloscope is showing you is a waveform like this, right? AC voltage. And it's showing you, in this instance, it's showing you a 60th of a second what's happening on that power source, that voltage, that force. So it displays signals in the time domain. In this case, it would be a 60th of a second, but you can change that time domain. So if you wanted to view 2/60ths of a second or 1/30th of a second, what would you end up seeing on that scope?
What was the question again? Sorry.
In this example right here, what we're looking at in this window is a 60th of a second, right? If this is 60 hertz,
Mhm.
Uh-huh.
if I told that scope, hey, I want you to show me what that same waveform looks like in 2/60ths of a second,
Mm-hmm.
show you this,
Waveforms.
2
Yeah,
seconds,
double it. Yeah.
right?
Yeah, you just double it. Yeah.
What are frequencies above 1 gigahertz generally called?
Microwaves.
Microwaves. And you married? Got girlfriend?
Yep.
So now you can go, like I like to mess with people and say, hi, sweetie, could you put this hot pocket in the frequency greater than 1 gigahertz generator? Huh?
Yeah, that won't get you any extra credit.
No, it's not gonna score you any points. Alternating voltage continuously varies in amplitude and periodically reverses polarity. Is that true or false?
True.
That's true. What does amplitude mean?
Yeah, strength of it.
Basically the height of the peak. Amplitude is just a value greater than this line. So amplitude could be this way, it could be this way, and it's changing throughout time, right? So this amplitude is less than this amplitude, is less than this amplitude, and then it starts to go back down. So the amplitude is continuously changing, and periodically, does it reverse polarity?
Yeah.
Yep, it's going in one direction here, it's going in the other direction here. Is the sine wave proportional to the sine of an angle of rotation in the circular motion?
Yeah.
Yeah.
True.
Yes.
True.
I should have taken that question out because it's junk. But what they're trying to say here is that if I had this same top sine wave, if I represented this same thing in a circle, starting right here, 0 degrees. And let's say we're going counterclockwise here. At this point here, at this peak, that's how many degrees right here? This one, what's this?
Oh, 90.
90, 180.
That's 90 degrees, right?
Yeah.
That same point on this circle, if I was representing this in a circle, would be right here, right? This is 90 degrees. And then 180. It's a really dumb question, but whatever. The peak value is the maximum value of a sine wave.
Big values. Yes, true.
Yeah, sorry.
Right here.
Mm-hmm.
The RMS value of a sine wave is equal to 0.707 times the peak value.
Sure.
Yep. There's your RMS. True. 5 kilohertz sine wave has a period of
200 microseconds.
200 microseconds.
Yeah.
Everybody agree with that?
How
do
did
we
you get?
Good question. On your formula sheet.
1 divided by 5.
Ah! Where's the period? Not on there?
Mm-mm.
I know.
Good grief.
Okay.
These are two period formulas, but they're not the formulas we need. So what is the formula? Period equals
1 divided by the frequency.
Yeah,
right.
which is 5,000.
So since that is not on your formula sheet, I would write that in there somewhere, unless you can remember it. T, which is period, equals 1 over the frequency. Except this looks a little, it's like lambda, isn't it?
Yeah.
Greek letter lambda. Let's get Greek on it. Woo! So in this case, period T equals 1 over the frequency. So it would be, how many hertz is 5 kilohertz?
5,000.
5,000.
5,000 divided by, oh,
No, it's backward. 1 divided.
what the hell am I doing? 1 divided by 5,000. Okay, and you get, and these, on all these formulas, you just gotta make sure you keep your units the same, all right? So this formula, T, would be the period in seconds. And the frequency would be in hertz, right? So if I put 1 divided by 5, I'm not gonna get the right answer, right? It would be 1 divided by 5,000, which gives you a number that looks like 0.0002. Is that right?
Mm-hmm.
Yeah, well, there's 200. Well, let's say 200 points.
Yeah.
-6.
Oh, so you were taught scientific notation on your calculator by John, probably, right?
Yeah.
Yeah.
Okay, that's fine. Do it however you want to. I'm more of a visual guy, so like.
Okay. No, that's fine. We just. Yeah. Sorry.
So on your calculator, you probably got something that looked like 200 E6 or something like that.
It's 0.06.
E minus.
Negative, yeah, -0.06. Yeah.
So either way you want to do it, this is how my brain works. Might as well run through this now. 0.000000000000. If I move it over here, oh, yeah. If I move the decimal place here, that's micro. If if I move it here, no.
That's
a
milli.
Milli, micro.
A milli, a milli, a milli, a milli, a milli.
eh.
We didn't know you sang too.
It's not singing, that's rapping.
My bad.
My bad. Milli, micro. What is it, nano,
Nano.
nano and pico? I don't remember. I always get nano and
Yeah.
That sounds right.
Right, so if the number is 0.0002, it'd be either 0.2 microseconds or it'd be, no, 0.2 milliseconds or 200 microseconds. Either way you strike it, it's the same number, 200 microseconds. 2K ohm resistor has a peak voltage of 10 volts applied to it. What is the instantaneous value of current at 62 degrees?
0.41 milliamps.
It's
4.41 milliamps?
Mm-hmm.
How'd you get that?
So you have to use Ohm's law to get the actual current, and then you take that times the sine of 62 degrees.
So what it's telling us is that the peak voltage is 10 volts. So instantaneously at 100 or 90 degrees,
getting
this is-
better.
thank you, extra credit. This is 10 volts. So that's an instantaneous value at exactly 90 degrees. And what it's asking us is at 62 degrees, so somewhere in here, what is this instantaneous value? And what's the formula for that? I guess we need to find current, right?
Yeah.
So what would the current be at peak?
5 milli.
5 milliamps. Yeah.
What's the resistance at peak?
2K ohms.
2000 ohms. And is that ever going to change throughout this whole sine wave?
No.
No.
Resistance is constant. So I'm finding the current at the peak value, I equals E over R, right?
Mm-hmm.
So it'd be 10 divided by 2000. What's that?
5 milli.
5 milli, 5 milli, 5 milli, 5 milli, 5 milli, 5 milli, 5 milli. .005.
Mhm.
And then what do we do with that to find it at 62 degrees?
Hmm.
Sine of 62.
It's a 5 times 62.
Mm-mm.
0.005 times sine of 62, correct?
Yeah.
All right. So
Yes.
if there's a
Thank
sine wave, if there's a separate sine wave up here showing you what the current is, this is 0.05, 0.005 amps. And we're trying to find what it is right here. To get this value, we have to take 0.005 times sine of 62, which equals
4.41.
4.41 milliamps,
Yeah.
or .00414.
Mhm.
Or 00441.
Yeah.
How you guys doing? You want to take a little break before you want to power through and get to the end?
You're done.
What's power?
Just power it right on through. You're gonna hear me rap more. Okay. A sine wave has a period of 100 microseconds. What is its frequency?
Oh, 10,000. Or 10K.
10,000 kilohertz.
Mhm.
1.21 gigawatts. Go back to our in this case, we're given a period. So 100 microseconds. I always write it all out. You don't have to do it this way, but 100 microseconds would be 0.0001, right?
Yeah.
Mhm.
Or 1 over the frequency.
Yes.
So you just
so
solve algebraically for F. You get F equals 1 divided by 0.0001 equals
one divided
10 GER. That'd be 10,000 hertz. And on your thing, 10 kHz, 10 kilohertz.
10 kilohertz. Yeah.
Sine wave, whose RMS value is 25, has a peak voltage of
Sine wave.
so we're given an RMS value of 25. We need to find this, the peak. Remember the formula that we wrote down?
$25. Yeah, there was 25. Yeah, it's 25 times 707.
Yep. V peak equals VRMS times 0.707. 25 times 0.707 equals
Yes, 17.675 volts. B.
It makes sense, right? Visually,
Yeah.
way No, we didn't do that right.
That's a peak. You gotta divide that by 0.707.
Right, we didn't do that right.
It's 35.36.
I was just getting ready to say that makes sense because it's about 70% of the peak, and I was like, oh no. So don't forget to
Okay, okay.
You're trying to find RMS.
don't forget to take a look at it and say, wait a minute, that doesn't make sense. Like I just screwed out the bit. But anyway, V peak equals VRMS times 1.414. Or you can divide it by 0.707. Either way, you get a number that looks like what? 35 point something or other.
It's always less than the value, right?
Mm-mm. The peak's always higher than the RMS.
Remember, look at the drawing, Louis.
Mm-hmm.
We're given this RMS value right here.
Yeah.
We're trying to find this. It's going to be bigger than 25.
I mean, big,
right?
yeah, big, yeah.
So 25 times 1.414. 35.35. Just out of curiosity, if you go 25 divided by 0.707, it's the same number, basically. 35.36.
36, yeah.
Okay, a sine wave with oh, I mean, sine with a peak value of 120. Has a DRMS of, oh, wait a minute. No, this is, we're not trying to find RMS.
It's just the-
Instantaneous voltage at 30 degrees of what? Well, what it's saying is at 90 degrees,
Hmm.
120 volts. So what is it at 30 degrees? Remember how to do that?
Yeah. 30 degrees. Yeah. 40 volts.
So what you're trying to do there, divide 120 divided by 3, right?
Yeah.
Not right. You have to do, remember it's a sine wave. So we have to take 120 times the sine of 30. Right? How come I can't get freaking trig on here? Here we go. Look at that.
Yeah. Hey.
Okay. Yeah. Okay. So I go 30 sine times 120. 60. Uno mas. A sine wave value of 50 volts has an RMS value of what?
35.35.
How in the hell do you know that?
50 volts times 0.707 will give you the RMS.
So peak to peak is 50.
Mhm.
Which means peak is how many?
Peak to peak, 25.
25.
Mhm.
Oh, okay, never mind, I did it wrong.
So what's our RMS value? It's going to be here. Whoa.
25 divided by 0.707.
Times 0.707. So it'd be 25 times 0.707. $17.675. Boom. Okay. All right. Any questions on everything that we've covered here today?
Yeah,
What?
a little too much information.
Too much information?
Yeah, I'm okay. Yeah, try to remember the formulas.
Yeah.
Thank you.
Yep. And so we'll take a quiz over chapter 1 on Tuesday. And I want you guys to come in for that. Everybody do that? We'll meet
Yep.
in room AIT 108. We'll do a lab after the quiz. And we'll take your next chapter homework assignment and move it back to the Thursday.
It definitely makes a lot
Definitely makes a what?
more sense now that you explained everything.
Good. Good, good. All right, so I'm gonna take chapter 2 homework. I mean 15, chapter 15. I'll move back to Thursday. Okay. I just don't want you guys to get like have to start thinking about the next chapter while you're getting ready to take a quiz on this chapter. Know what I'm saying? But that being said, all the future chapters are open, so if you want to work ahead, you're welcome to. Okie dokie.
All
And it
right.
probably, the way it's looking here, that's probably how what we'll shoot for week to week is homework due on Thursday, come in Tuesday, take a quiz, and we'll do a lab. So then the next Thursday, we got homework due. The next Tuesday, we'll come in to the lab and take a quiz and do a lab. Sound good?
Sounds good.
So generally speaking, and this is probably gonna change, because nothing can ever be easy, but generally speaking, we'll plan on doing Zoom on Thursdays and in person on Tuesdays. But don't hold me to that, that might change. Okay,
Okay.
everybody understands to come in on Tuesday, go take this quiz?
Yep.
All right, bring your, make sure you bring your parts kits on Tuesday.
Okay.
Let's see what that lab is looking like. Whoa. What the? Stuff. What the? This is not even right. I don't even know where it's at. Oh. Yeah, it looks like all we're gonna be doing is some scope. So, anyway, yeah, just bring your parts kits on Tuesday. Let me know if you need anything before then. Shoot me an email. Unless you guys have any other questions, we'll call it a day.
Hey, Zach, I got
Ah!
a question.
What?
No, can you tell me the, oh, and that's easy for me, but can you tell me the formulas again? Just to make sure I write it correctly. I know, but it might be in the book too, but sometimes I don't understand the book very well.
Yeah, I will. And here's the other thing. I'm recording this. Did any of you guys go on the recording from Tuesday's class? Not that you really needed to, but
Yeah, I went a little bit last time, yeah.
if tonight at 10 o'clock, you're like, oh crap, you know, because, you know, I'm sure all of you, like when you lay your head down at night, you're thinking about me, right? And you're like, oh crap, what did he say about VRMS? Well, there's going to be a video on YouTube that the link will be on your Google Drive, right? That you can go back and you can use that. But for right now, yes, I will tell you what those formulas were.
Yeah, I remember that was drawn in a VR Mac, VR MS. So I
Yeah,
just
so
want
what
to
do we
make it
have?
sure to write.
And,
So therefore, B was B RMS is voltage times 0.7 or 7, right?
Yep, I'm gonna draw it out too, because I'm a visual learner. So VRMS is gonna be this red line, right?
Mm-hmm. Mm-hmm.
We'll make the peak.
Mm-hmm.
Right here. And that's this amount. The peak to peak
Mm-hmm.
is gonna be this.
Okay.
And VRMS is this. Right?
Okay.
So the
Mhm.
formulas will be VRMS
Mm-hmm.
equals V peak
Repeat. Yeah.
times
Times.
0.77.
Okay. Okay. Just to make it sure. Thank you for that one. Okay.
V peak equals VRMS
divide, is it?
times 1.414. Or it also equals VRMS divided by 0.707. Either way you do this, it's gonna work. Okay,
Okay. That's what I got us confusing because I write down the first one about dividing. So I'm making sure. Thank you very much for those two.
sure.
And the other
And
one,
then
the
the other one
this
was-
peak to peak,
Yeah, V peak to peak is
peak times 2, right?
V peak times 2.
Okay. That makes a lot of more sense. Now this explains everything literally. So
Okay,
yes, that's great. Thank you very much.
no problem. Anything else?
Thank you. No, now.
Now, okay. Hey,
Thank you.
Louis, can you stay
Yeah.
after class? for a
Yeah.
minute? Okay, I need to talk to you.
Yeah,
about
I
class.
can stay. Yeah.
Okay,
Yeah.
all right.